Hello and welcome to another Quantway Core video. Today we'll be exploring lesson 3.4 in your book, which starts on page 349. Please note, however, that we will not be doing the exact problems in the book. You need to click on the PDF located in Blackboard that will show you the revised questions that we're looking at, although the basic premise will be the same. Today we're going to be looking at a formula, and this is a little bit more of a complicated formula than maybe we're used to dealing with. So what this formula is going to look at is calculating braking distance and in your car. And what that's talking about is, let's say you're driving down the road in your car and you see a deer run into the road. So you stand on the brakes. You push on the brakes pedal as hard as you possibly can. Well, needless to say, that car is not going to come to an instantaneous stop. It's going to take a little while to slow down. And while it's slowing down, it's going to continue to travel a certain distance. Okay, and that distance that it travels is called the braking distance. That's the distance the car travels between when you step on the brake pedal and when the car comes to an abrupt halt. So there's many things that might affect this distance. The book asks you to brainstorm on about a bunch of them, and it's asking you to think of variables that might affect this. And of course, variables, remember, are anything around us that might affect the outcome. So let's say if a car in one situation stops in a really short distance, but a car in another situation takes a really long distance to stop, what might be different? And you don't even need to know anything about cars for this, just to think about cars and roads and what kind of things might be different. All right, so as I mentioned, the way we're going to be doing the lesson is a little different than the way it's printed out in the book. So I took the number 2 question from the revised version, which again you can find as a PDF in Blackboard, and reproduced it on in this video here. So what this is asking us to do is think about unit conversion. So remember last week we talked about dimensional analysis where we did conversions that involved units. So the main part of this lesson is not going to be dimensional analysis, but it's going to come up to help us out with this one thing here. And here's how. This formula that we're about to talk about has us plugging in our speed in terms of feet per second. Okay, and that's a little different because when you're driving in the car, you look down at your speedometer and it tells you your speed in miles per hour. But the fact is, each second that your car is driving, you travel a certain number of feet. And so we're going to have to do a conversion from what the speedometer tells us to figure out how many feet we're traveling each second. So what that means is we want to, what our target rate is some number of feet over 1 second. Okay, so remember how this works. We want to start with a rate on the left here that has feet on the top. We're going to have to do some conversions to probably get the bottom. And we see right up here in the paragraph, in the question, it gives us a rate with feet. So we could start out with 5,280 feet and 1 mile on the bottom. So the numerator, the top, is already all set here, but we're going to have to put some other rates in here, probably more than one, and put some units on here to cancel out my mile and turn it into seconds. And so we'll use this one rate that we're given here, and then also what we know as far as converting between minutes and seconds and hours to turn it into a number of feet per second. All right, so here is the formula that we're going to be working with today. And this is the formula. This formula estimates the stopping distance of a car. And I use the word estimates because the only truly accurate way to determine the stopping distance of a car is to get a really long tape measure and go out somewhere and slam on your brakes. Because there's lots of other variables in play that this formula might not take into account, but it definitely takes into account the big ones, and it will do a good job of approximating. Now, this formula can be found on the top of page 350, and what I'm going to go through here is pretty much what they go through in the book, but you'll have the benefit of hearing me actually do the talking, and I'll go into a little more depth. So the thing that this formula is calculating is braking distance, and that's what that little d stands for there, is braking distance. And the braking distance in this formula is in feet. So that's my d, is braking distance in feet. So that's going to give you a distance like 200 feet, which is the amount of feet that your car travels between when you slam on the brakes and when the car comes to a stop. So moving over to the right side of the equation here, we see a big V, and it has a little 2 and a little 0 sort of hovering around it there. So let's take a look at one of these little numbers at a time. So V sub 0 is, what that means is our initial velocity. And that little sub 0 often, when put next to a variable, kind of means the initial value, just like you start counting at 0. So that's the number you start with. And in this case, the velocity, this is the velocity you're traveling when you first apply the brakes. So in other words, you're driving along at some speed and then you slam on the brakes. So right at that instant before you slam on the brakes, that's your initial velocity. And the key to this, and this is where the dimensional analysis will come in, is this is in feet per second. So we're going to have to come up with feet per second, a number of feet per second to plug it into this formula. So, and what the little 2 means is that just means squared, just like when you square any number. So let me show you what I mean. So let's just say our initial velocity was 14 feet per second. That means that our initial velocity squared is 14 squared. So that just means squaring it. And you see the little 0 goes away. We don't do anything mathematically with that. There to show that that V is our initial V value. Okay, moving on to the bottom of our equation, the denominator. We have a few different variables here. So the first variable I want to look at on the bottom here is this little g. What this little g stands for is the force of gravity. So gravity is always pulling down on us. It's what keeps everything sitting down on the earth. It's what's keeping me in this chair as I'm recording this video. And it can actually be measured with a number. And that number is 32.2 feet per second squared. And what that means in a nutshell is that if you drop something in midair, it will accelerate towards the Earth at the rate of 32 feet per second, or each second it will be traveling 32 feet per second faster than the previous second. And we don't need to focus too much on the intricacies of these units because the way this formula is set up, the units kind of take care of themselves once we have everything set up to begin with. And you may wonder, why do we need to think about the force of gravity when we're thinking about braking? Well, I don't know what answers you got for the question for number 2 there, or for number 1, I'm sorry, but think about this. When would it take you longer to stop? If you're going downhill or if you're going uphill? So if you're going 50 miles an hour uphill or 50 miles an hour downhill, which is going to take you a longer stopping distance? And the answer to that is based on the fact that gravity is a force that's either working with you or against you. Okay, moving right along to this little f here. So what the little f stands for is a coefficient coefficient of friction. And without getting into the details of what that means, a coefficient of friction, think of it this way. Well, let me back up for a second. So this is a number somewhere between 0 and 1 approximately. And this will be given to us. We're not going to have to calculate this. We'll just be told what it is in a particular situation. But think of it this way. So friction is what keeps the car on the road. When you don't have friction is when you're driving on ice and the car slips all over the place and you try to turn the wheel, and since there's no friction between your tires and the road, the car continues to go whatever direction it wants to go. So friction is a good thing when you put on the brakes. And so for number one, you might have thought about, what the road surface is like, or what your tires are like, or what the condition of brake pads are like. There's friction in all of those things. And the last variable we're going to look at is the big G. As if one G wasn't enough, we have a little g and a big G. And what the big G is the grade. That is the grade of the road. And that's another way of thinking about the angle of the road. So this kind of ties in together with the gravity thing and calculates and takes into account whether you're going uphill or downhill. And this is a percentage value as a decimal. So for example, if you had a 45-degree angle like this, that would be a 100% grade. And if you had a less steep angle like this, it would be a much lower percentage. It might be a 10% grade. And that is based on finding two parts on the hill and comparing the vertical and the horizontal values. So this is 100% because this vertical value is 100% of the horizontal value. This is 10% because this vertical value is 10% of this horizontal value. So that's just a curiosity. You won't need to know the details of this grade business, but you will need to know that when they give you a grade, it's going to be a decimal, probably a pretty small number like 0.01. And that's what you're going to have to put in for the big G. So what number 3 is going to ask you to do is to simplify that big ugly formula that we just talked about. And I'm going to give you an example of what simplify a formula means. And part of what that means is that they're going to give you some of the values here. They're going to give you the little f and the big G. And we remember that we actually already know the little g. So that means that there's some values that we're going to plug in and just leave there. So that means we don't have to plug everything in every time, that the only thing that's going to be changing is the v, which is the only variable that we're not given a value for. So let me give you an example of a simplified formula. So here is something that has nothing to do with braking distance. But what it will help us do is look at how to go about simplifying a formula. So what this formula right here does is it calculates the volume of a cylinder. So if you know the height and the radius of a cylinder, you can plug it into this formula and come up with the volume. So let's suppose that we have a cylinder whose height, we know that we want a cylinder that has a height of 11. Okay, a height of 11. And what we want to do is figure out the volume of cylinders with different radiuses that have that height of 11. So this is the full formula here, but we're going to simplify it because we're only dealing with cylinders that have a height of 11. And furthermore, we know what pi is. We know it's about 3.141. And so we're going to plug in the numbers we know. We don't know the radius, that's the unknown value, but the height is 11. So if we go into our calculator, we can multiply these two values here, and we get the volume equals 34.2 56r squared. So this is a simplified formula here. So every time I calculate, say, okay, what is the volume of a cylinder with a radius of 8 and a height of 11? All I need to do is plug the 8 into the r for the r variable in our formula, because I've already combined the pi and the 11, which aren't changing. So this is an example of a simplified formula. It saves you some work.